Okay, so again, I'll just say it quickly. You have a data list in a data memory, which means make an array. It's in bytes this time, not in words. So that means the largest number would be like 100, and if it's 128, 127 would be the largest number. The smallest number would be negative 128. You have to put the A0 is going to be pointing to the beginning of the array. So you've got to define that. And you've got to put the length of it, which means you're not going to have a 0 at the end to tell the length, because the 0 will be a valid number in the array. So therefore, you can't use 0 as a marker for the end, since any number is valid. So therefore, the length you have to know. So you'll just type in the length. Like if it's 10 numbers, you'll type in 10 and put that in A1. That'll be hard coded in. And then you have to find the largest number and put it in V0 and display it on the screen. You don't have to do a flowchart or comments. You also don't have to do. But the trick here, first of all, you have to test. Well, sorry. In the previous one, right? What is the strange case here? The strange case here is the negative. They're all negative, for example. I always test that they're all negative, and people a lot of times fail on that. There should be no reason, though. The negative numbers deal with the same way as positive numbers. There's no, in other words, can anybody tell me what important command you're going to use or instruction you're going to use to distinguish if a number is larger or smaller than another number? Anyone remember the specific instruction?
SLT.
SLT, great. So for those who don't know, write it down. SLT is what you're going to use to say set less than. That'll tell you if one number is bigger than another number. And that's the main thing you're going to have to use here. And then you have to check, did I get a 1 or did I get a 0 on that check comparison? You also have SLTI, which might be useful, but SLTI just allows you to have an immediate. Okay, that's enough for lab 1, or 2.1. 2.2, though, is more complicated. So write a program that's a calculator, but it's not going to do division. It's just going to do here star, minus, and plus, and the @ sign will mean equivalent to equals. Will be ending. So that means I could do 1 plus 1 plus 1 plus 1, and it should print, and then @ and it should write 4. So far, so good. That you should know how to do. As far as you're going to have to use, system calls to print. You can also have to print, enter value as a message, and then enter another value, and then you have to say enter opcode, or you could do the opcode in the middle between the values probably. So enter value, enter opcode, and then again enter value. So you're going to have to define these strings at the beginning as arrays essentially. And you're going to use them every time you between the input of the numbers and the symbols. Now, in order to check what symbol he gave you, you're going to have to store this symbol in a register. Now, how would you do that in C++? If you wanted to have a symbol in a character, in other words, you have a variable of type character, how would you store the symbol asterisk in that character? What would you write in C++? In other words, if you wanted to put the letter A in a character, or how would you put the letter A in a variable? How would you put that in?
You mean with single quotes?
Exactly. Thank you, Avraham. In single quotes, you would write my variable equals single quote A, single quote, semicolon. So the same thing here with the asterisk. You'll use single quotes. When you have a single, I always teach this rule. When you have a single character, you have single quotes. When you have multiple characters, you have double quotes. So that's fine. You're gonna have to compare what symbol he gives you to these 4 symbols. So far, so good. That's just branch equals,
How are you loading the symbol into register? By like an add I or what?
Yeah, you could use an add I. Exactly. Add I, single quotes, asterisk, single quote. Now, as you can treat it the same way you would in C++. You could also look up on the ASCII table what asterisk is, and maybe it's, let's say, 43. So then you could write 43. But that would be silly, but that would work. So the compiler will translate your asterisk into 43. Obviously, in the computer, it has to only work with the number, but you're allowed to type, asterisk. So yeah, you can use add I. You could also use li, and then you're going to display the result. If he doesn't want to, if a non-termination action code is requested, that means star, minus, or plus, then the computer will again say enter a value. So if you think about it, you have a series of printouts, which is a loop, which is enter value, enter opcode, enter value, enter opcode. It's repeating. Always don't think of it as enter value, enter opcode, enter value. That's not going to repeat. That'll screw you up. It's not all three. You don't want to do enter value, enter opcode, enter value. You want to do enter value, enter opcode, and then repeat. And if the opcode is in other words, if the opcode is at, then you immediately go to print. So if the guy would type 1 and then at, you would immediately print 1, because that's the value you have at that point. If you type 1 and then plus, so then you would see that it's a plus, and you would say enter value again, and then you put a 1, let's say, and then again enter opcode, because you got to tell you, are you done or are you not done? And if he says a plus, then you go back and loop again. If he doesn't say plus, then you print what you have. So far, so good. That doesn't sound complicated. You're going to obviously have integers, but a problem may occur. Here's the complication. When multiplying two numbers, a result greater than 32 bits may be received as the result. In other words, the result may be larger than 32. In other words, if you multiply a 32-bit number by a 32-bit number, what's the largest result you could have?
64-bit number.
Exactly, a 64-bit number. I want to show this to you. Just a second. I'll show it to you in an imaginary world of words that are smaller. So just a second, stop share. Wait, did anybody come late? He wants me to mark them down. No, I don't see anybody. Okay. Okay, so look here. If I do, let's imagine I have a word length of 2. So I do 1, 1. Here, let's put some spaces. 1, 1 plus 1, 1. So what am I going to get as my result? I'm going to get, a 0 over here. And then I'm going to get a 1 over here. And then a 1 over here. Is that right? That makes sense? Because the 1 and 1 is going to be 0 plus the 1. And the 3 ones will be a 1. And then a 1 carried. So that's 3. Oh, I did addition. I did addition. So addition is 3 and 3. 3 times 3 is 3 plus 3 is 6. And that's 6 here. So that's addition. So the maximum you'll get in addition, actually, you'll get a possible 1 bit overload. Well, we're not going to worry about that. But in multiplication, let's say I do the same thing, 1, 1, and then I did 1, 1. So I'm going to obviously get what is 3 times 3 is 9. How do I write 9? I write it like this: 8, no 4s, no 2s, and a 1. So you see that I have a 2, the maximum value 2, and I'm going to get 4 digits. But really, I did it wrong. Really, there should be a 0 here. Let's try this now. A 0 here. That's really what I'm going to get. And really what I should get is like that, right? So actually, but it doesn't really matter, because I still have I still went outside of the range, because it's in my imaginary world, it's only 3-bit range. And in order to write 9, if I just look at the result, if I'm in a world of only 3 bits, what am I going to see as my result? When I multiply 3 by 3, I only can look
1.
at, I'm going to look at 1. I'm going to see 3 times 3 is 1. And that is going to say to me, something went wrong here. So that's called an overflow. Now let's try another example. Let's try,
For when you shift for multiplication, it needs to have a sign bit on the left side. You said that it needed that those
well,
two zeros.
usually you shift something that you started with. Right, it's true. If you shift a number, you're making a very interesting point. If you shift a number, you could start off with a positive number and get a negative number. You're right. That could happen. If it's a small number, you're okay. In other words, right. But by the way, you're wondering why we do that. But if it's less than 16 bits, you're basically going to be okay. You know, they'll all be zeros on that if it's a positive number. But you're right. If it's a negative number, you're right. You're going to lose the sign bit when you shift. It could cause you a problem. With small numbers, positive or negative, it won't be a problem. But I'm not worried about that right now. We're not going to shift. We're not multiplying using shift. We're multiplying using a mult command. There's a command which looks like this. Right. Looks like this. Mult, and then you write like $T0, $T1. And that's it. That's the command. Don't do any other mult. There are other ones. There's mult. There's another one called mul, M-U-L, which takes 3 registers. Do not use that. Oh, that's not a real command. It's a pseudo command. Only use mult. Now, what this is says multiply these 2 numbers. But where does the result go? So the result goes into a special register called LO, L-O, and I'll talk about it in a minute. But first, I want to explain this. Let's say it's 2 negative numbers. Can anybody tell me what this number is in 2's complement? Assuming a 3-bit
Negative.
3-bit word, a -1, exactly. The one thing you have to remember of 2's complement for your whole life is that all ones is -1. If you remember that, you're okay. You'll be fine with every problem. So if I multiply -1 times -1, what should I get? If the world is good,
+1.
I should get +1. Well, let's see what's going to really happen. So if we do 1 times 1, what are we going to get? Actually, you know, -1 times -1 won't give us a problem. What will give us a problem is, I don't have a good example. I'm not giving you a good example here. Well, suffice it to say that the previous example, I'm not going to do a negative example because I don't want to waste your time. But it can also be a problem with that. You know, that one would work actually. But if I have, again, if I have, you know, a 4-bit word and a 4-bit word, I'm just trying to explain the problem. But a 4-bit word and a 4-bit word. So now I have all of a sudden the number 1 and 2 is 3. I have 7. 7 times 7 is 49. So, right? Isn't that right? 7 times 7 is 49. So obviously I'm going to have a lot more bits than 4. So I'm going to have what's called overflow. So what we have is like this. So let me show you the Mars Explorer, the Mars, not Mars Explorer, the Mars simulator. I wish I could show you the Mars Explorer. Has to come up. Yeah, here it's coming up. Pretty amazing they're going to send a helicopter on Mars. I don't know if it's already gone launched, but I just hope there's no storm that day. It'll get ruined. Stop share. Share screen. Mars. So look over here. Here you see what I told you about, the low register. Notice there's extra registers here. These are the 32 registers. Then there's also low. Low is where the result is going to be. High is actually going to be where the overflow is going to be. If there is an overflow. I mean, well, the overflow, whatever. In other
I
words,
couldn't hear what you just said when you moved about the
Sorry.
high.
the high will be where the overflow is. So I'll show you, for example. What was it I did new? To save. So if I do, for example, LI 214747 954. Oh, I got to put it somewhere. Into $T0. And then I do $T1. I do 11. Now that's a big number. And then I do mult $T0, $T1. Okay, so now if I do run or compile, now look, just look at the high and the low. They're both 0. Now I run it and they're not 0. Well, high is 0, but low isn't. This is a funny example, but yeah, before I go to this example, let's do a slightly bigger number. Okay. Or yeah, I don't know, 17. That's not big enough. Here. So there you go. You see, I got something in my high and something in my low. Now look at the low. Do you see, what is it, positive or negative?
Negative.
Now is that weird that it's negative? Because look, I multiplied 2 positive numbers and I got a negative result. I also got an
Can you
overflow.
explain what high and low again is, please? I don't know if you said it before.
Yeah, I said the
So-
low is the result. In other words, I started with a complicated example. Let's start with a more simple example. 17 times 2. What's 17 times 2 is 34. So let's see if I get 34. I got 34 in the low. So the result is for my low. The high is the overflow. It's 0, so there's no overflow. In other words, with a positive number, I would expect the high to be 0. Let's try with a negative number. Negative 2 and multiply. And now what do I see? Negative 1 and negative 34. Why negative 1 in the high? Anybody tell me why there's negative 1 in the high? So you remember this term called sign extension? You learned sign extension. Can anybody tell me what sign extension is? Very important concept. I'm sure Avi talked about it, but you also learned it in your previous course. What's sign extension? Nobody knows? Okay, so I'll have to tell you. Sign extension is that we take the sign sometimes of a number and we extend it into the empty bits. In other words, if I multiply like, 0, 1 times 0, 1, I might, and I want to put it into, let's say I take this number 0, 1, and I want to put it into a 32-bit register. So I'm going to fill up the left side with zeros because of a positive number. And if I put the number -1, I just want, let's say I have just 1, 1 as my -1 number. But I'm going to put in 32 bits. I'm not just going to leave it as 1, 1 and put zeros over there. I'm going to extend the sign to fill up the size of my register or my whatever my word length is, so that the number will maintain its correct form in 2's complement. I got to extend the sign. I've got to fill in the empty space. I can't let it fill in with zeros. I got to fill it in with ones so that it will still be the negative number that I wanted if it was a negative number. So in order for this 34 to be 34, well, the whole, if I would look at all the bits of this low, like let's see if I can do hexadecimal values. So look at this number. Look how -34 is written. You see it's F. What is F? What is F in hex? 15. What is that in binary? Come on, guys. I know it was long vacation. What's 15 in binary?
1, 1, 1, 1.
Thank you. 4 ones. So this is 1, 1, 1, 1, 1, 1. Lots of ones, 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 until we get to this DE, which is the beginning of the representation of the value -34. Now, if I would just ask you what's FDD in 2's complement, you would tell me -34. And if I would ask you what FFDE, you would also say -34. And if I'd say FFFFFDE, you'd also say -34. All of these F's here are just extra ones to fill in the register, because if there'd be a 0 anywhere along here, all of a sudden the number would change. I got to put as many ones as necessary to fill in the area that I'm looking at so that it will still be 2's complement and it will still be that number. That's called sign extension. In Hebrew, hamshachat siman. Now, what's going on here is that the high and the low are actually the high is really another name for it would be the most significant bits, the high order word of multiply product. In other words, it's the most significant bits. Really what's going on is when I multiply two 32-bit numbers, it's giving me space for a 64-bit result because that's the largest result. And how is it giving me that space? By combining two registers such that the high is the left side and the low is the right side. And therefore, these F's don't stop here. They continue into the high. And that's why I have all these F's in the high, because it's essentially just the continuation of the number. The sign extension is fulfilling this with ones. So that's why when I look at it in regular value, I see a -1, because if I look at FF, all those F's in isolation, that's what the simulator is not combining these two registers. It's just looking at each register in isolation. And in isolation, all those F's translate to a -1. And all those F's followed by the DE translates to 34. So that's sign extension. So this is a case where I multiplied two numbers and I did not have overflow because the result was negative and the sign extended into the high properly. But if I multiplied this by some, I don't know, let's go back to my example. 2, 1, 4, 7, 4, 7, 9, 5, 4. Let's see what happens now. Ah, well, that's interesting. That's interesting example. There's no overflow here because I have a -1, which is what I should have, all F's, and the result is negative. That's good. Well, let's make this number a little larger. Ooh, still no overflow. So I have a question. Is there overflow here or not? What's wrong with this result? I multiplied minus 11
Positive numbers.
times a positive number. I should have gotten a negative result, right? Did I get a negative result? No, I got a positive result. But if I look just at the high, it looks like fine. It looks like I got a negative. If I would have compared these two numbers, if I would do the following algorithm, just take two numbers and check what the result should be. The result, since the signs are cross signs or mixed signs, the result should be negative. And check if the high is only -1, then there's no overflow. Except there is an overflow because I got a positive result somehow. What happened? Can anybody tell me what happened here? What do you think happened?
You overflowed by 1 digit.
I overflowed by exactly 1 digit. And what digit was that? Was it a
The
value
right-
digit or a
that's the
sign
high.
digit?
So it was a
What?
thinking.
Well, I lost the sign. Then the result was positive because I lost my sign. My sign got overflowed. In other words, if let's say I do this sum multiplication of two numbers and I get the following: 1 1 1 0 1 1. Wait, let's see. Yeah, 1 1 0 1 1 1 1. No, sorry, 0 1 1 1. Okay, what number is this? Is this positive or negative? This number in 2's complement.
Negative.
Negative. That is a negative number. What if I told you that my word length was 4? So that means I would have the low would be this, would be positive, and the high would be this. So I would have a positive result, and then the high would be negative, but the low would be positive. Anyway, that would be an overflow. What about, I had the following. Try this number. This number is also negative. But if my word length is 4, then my low would be positive and my high would be all ones. And it would look like -1. The high would look totally good. It would look like it's just sign over here. It's just sign bits. And it is just sign bits. But the low is missing its sign because it looks like positive. I need at least 1 1 over here to maintain the negativity of that number. I can push away. If this is my number and I have a 5-bit word length, then everything is fine because I don't have overflow now, because when I divide it up into 2 parts, the 5 and the 5, I maintained one of my sign bits. I kept at least 1 1 over here. But if my number would be this, and I would have an overflow. So in other words, 2 things can happen. Either you can have an overflow of a value bit and a sign bit, or you can have an overflow of just a sign bit. What numbers you're multiplying. So how are we going to detect such an overflow?
I'm having a hard time visualizing it because I don't understand how to use high and low. Are we able to see what we can do with it?
All right. Well, I can only the best way to tell you how to use high and low normally is by example. So I can give you. I did an example. I can give you another example of that. I mean, if that's what your question is, how do you use the high and low? So I just multiply numbers.
Right, but then we saw what the problem was. But what's like where like that we could, meaning what happens when you have a really big number that's I don't know 50
That's
bits.
exactly what I'm discussing. That's exactly what I'm trying to explain. For example, here, if I have small numbers, 11 and 13, so the result is on -143. And that's my low, and that's my high. But the main point to understand is that the high and the low are really the in order to get the full result of a 32-bit, this is a 32 bits and this is 32 bits. The result is 64 bits. We don't have registers that are 64 bits. So how do we create a register of 64 bits? Very simple. We take two 32-bit registers and we combine them together and we view them as one long number. And we're going to call the most significant section the high, and the least significant section we'll call the low. Does that help you visualize it?
Yes,
words-
I understand. So what happened, like what, so how do we use high and low? Like you print out low, you print out high. How
Exactly.
do you come
I would
together?
print out,
I'm asking.
no. How do you print it out? Oh, so I'll say it like this. As far as printing, we are only able to print out a register. So therefore, therefore all we're going to print out is the low. That's all we're going to print out. What about the high? I mean, we could print it out, but it's going to be meaningless if there's an overflow into the high. In other words, on a theoretical level, we have the result in the high and the low. But in a practical level, all we're interested in is the low. And if there's anything in the high of the actual result, we're going to call that an overflow. So we're never going to print the high. We're only going to print the low. But sometimes when we print the low, it'll be a faulty, it'll give the impression of a different number. Like in this case, it would be fine. But if I would write a larger number, 214747954. So if I would print the low in such a case, it would be misleading. It would not be the right result. So instead of printing it, what your program is going to do, instead of printing this large number here, which is the wrong result, that is not the correct answer for this multiplication problem. So instead of printing that, you will print error. You will just print error. In other words, only when the result fully fits into the low and the high is not needed will you print the result. Does that help you? That maybe I didn't make that clear before.
I mean, no, I understand the problem, but what's the solution really?
Well, that's where I'm going to.
You said print-
That's what I said.
okay,
We need to detect overflow. That
Right,
is
so
exactly the question.
let's
How do
detect.
we detect overflow? We need to detect when the result in the low is valid and should be printed, and when the result in the low is invalid and we should write the word error. So I thought about this for a long time, and I came up with a simple algorithm. There's many ways you could try to do it. The most obvious way is to say, well, compare the two numbers, and if the result should be negative, make sure the result's also negative. But I just showed you an example where that doesn't help. So the correct algorithm is the following. I'll show you. I'll show you the correct. I'll just give it to you because, or somebody could try to think of it, or we'll work it out together. It's always a question in teaching. Just a second. Share screen. First thing, I had to make sure everybody understands the problem. Is there anybody who does not understand the problem? That's the main thing. To understand the problem. Now, how do we solve this problem? So we simply write like this. If, I'm going to write in pseudocode. If the result is negative, how do I say is negative in mathematical terms?
Less than 0.
Yeah, less than 0. If the result is less than 0, it's negative. So let's write in comments. Result is negative. If the result is negative, then what? Then we have to do another if. What should the case be about the high? Actually, I'm going to change this is actually low, right? If the result, when I say result, I mean the low register. If the low register is negative, then what should the high register be? Remember, in
Negative 1.
2's complement, what should the high register be?
Also negative.
Well, negative is not enough. It could be like
Negative
negative
1.
34.
Negative 1.
It has to be exactly -1, which is what? All ones. It has to have just sign. It has to be exclusively sign bits, no value bits. So if the high is not equal to -1, then what is it? If it's not equal to what it should be, then what is it really? Then what have we got?
Overflow.
We've got overflow.
So we can't actually multiply 32 bits by 32 bits to get 64 bits as of now in our case.
In our program, in the program that you're going to write for lab 2.2, you are going to be limited to a 32-bit result. Yes, actually even
see.
less,
Okay.
30, like a 32 and 2's complement, which is only 31
And
bits.
you want us to check to see if the result had overflow, basically, for the problem.
Yes, you have to check. You have to print. Or whoever checks. I have a checker now. Whoever checks your targil, I'm going to give him mathematical questions to check for overflow. Now we're not done. That's only for negative. That's only if the result is negative. What about the if? No, else. I can say else, or I can say if result is like not less than 0, which is equivalent to, remember, whenever you reverse a comparison, it's the opposite plus equals. If the result is, all other cases are if it's greater than or equal to 0, you could just do, you could just write else. But I'm trying to be extra clear. In this case, low is positive. By the way, we can say, therefore, that 0 itself is also positive, right? In 2's complement, 0 is by definition positive because it starts with a 0. That's just a side point. Just a trick question I like to ask. What is 0? Is it positive or negative? So the answer in math, who knows? But in computers, it's positive. So now what is our question? If the result is in fact positive, the low is positive, then when is there going to be an error?
High is negative.
No.
Well, high is anything but 0, basically.
Oh, that's 0. I didn't explain this, but good that you got that. The high has to be only sign bits. What are sign bits? Sign bits are
All zeros.
are 0 for a positive number. So if the high is not equal to 0, then overflow error. So that's your algorithm. You're going to multiply the numbers and then check the low and check the high for these cases. And if you have an error, you're going to print error. No other algorithm that I can think of works as well. I mean, you could try. You see, I gave you an example where you check the signs and we got the right result. You'd have to also check the high. You can always have to check the high and the low after the multiplication. Whatever you do, you could check before also, but it doesn't really matter. People have done other things, but this is the most efficient way of doing it. So that's it. Why don't
For
you?
comparison for high and low, I just use it as I would use the registers, $sign T0.
Oh yeah, thank you very much. Good question, Chaim. How do I compare? The compare is exactly like the low, except if you notice, well, the low, when we saw the Mars registers list, high and low are not real registers, are not registers that you have access to. There's no dollar in front of them. They're not part of the 32. So there's a special command that I have to show you, move from low. And what you do is you just write move from low $, T3. And what that means is copy the value in the low into T3. And then you can work with T3 as though it's your low, because you can't work directly with the low. You're not able to. Move from high, similarly, $T4. So you'll do something like that to actually get the low and high into workable registers, because you can't compare directly with a low. When you do you're gonna what command are you gonna do your comparison with? What instruction?
SLT.
Branch if equal. Or B not equal, B any.
Well, no, you want to do less than
For
0.
which one? For the less than
Right.
0, you need to set less
Right.
than or something like that?
For the first one, less than 0, you're going to have to do an SLT and then check the result with a branch. But here you could do, well, yeah, here you could put -1 into a register and then compare it directly with a branch not equal. Right? You could just copy you could copy into some other register, let's say I don't know, S1, you could put -1 into it, and then you could compare your high to your S1 with a branch not equal. So you'll do an SLT and a BNE. Anyway, that's for you to translate this into MIPS. All right, so I'm going to stop the share and I will make breakout rooms, and you guys can, I suggest you start 2.2 right now, because 2.1 is actually easy, pretty easy. But you could start 2.1. But if you want me to help you with 2.2, now's the time. So let me stop the recording.